Hello friends, let us now learn some important points about photoelectric effect. So, when an incident photon strikes with little energy, when an incident photon with little more energy than the binding energy of K shell electrons encounters or strikes one of the electron, this X-ray photon will eject the electron from its orbit. The photon will completely disappear, giving its all energy to the electron. Most of the photon's energy is used to overcome the binding energy of this electron, and the excess energy is given as the kinetic energy to the electron. The electron is now free of its energy debt and it flies off into space as photoelectron. Thus, the electron becomes a negative ion and is absorbed immediately, almost immediately, because charged particles have little penetrating power. The atom is left with an electron void in the K shell. So, this is the electron void in the K shell. So, the only for an instant, because the electrons immediately drops into the void to fill the K shell. The electron usually comes from the adjacent L shell or occasionally from the M shell or rarely from even outermost shell. As the electron drops from the outer shell into the K shell, it gives up some of the energy in the form of an X-ray photon called as characteristic radiation. The amount of energy is the amount of this X-ray photon is characteristic of each element, and the radiation produced by movement of electrons within an atom is called as characteristic radiation. When K shell's void is filled by an outer shell electron from the same atom, the atom is left with a deficiency of an electron in the outer shell, and this remains as the positive charge. So, if the free electron from another atom fills the void, then the atom becomes positive ion and the result is the same. So, for the photoelectric effect yields three endpoints. One, it yields photoelectron. Second, characteristic radiation. And third, positive ion which is deficient of an electron. Then the next topic is probability of occurrence of photoelectric reaction. There are three simple rules governing the probability of photoelectric reaction. Number one, incident photon must have sufficient energy to overcome the K shell binding energy of the electrons. If you take an example, the K shell binding energy of iodine is around 33.2 kilo electron volts. The X-ray photon should have an energy more than 33.2 kilo electron volts to eject the electron from the K shell. The photon may interact with L or M shell but not at the K shell. Second point, the photoelectric reaction is most likely to occur when the photon energy and the electron binding energy are nearly the same, provided the course of photoelectric effect is greater. In fact, the photoelectric effect occurs when the photon energy is approximately equal to or just more than the electron binding energy. In fact, if the probability of photoelectric effect decreases if the photon energy increases. So, as the photon energy increases, the probability of photoelectric effect decreases. If the photoelectric effect is inversely proportional to the third power, this is third power of energy and is expressed in the mathematical form. Photoelectric effect is inversely proportional to the energy cube. This is cube, not square, it is cube. Then the tighter the electron is bound to the orbit, the more likely it is involved in photoelectric reaction. The electrons are more tightly bound in high atomic number than in low atomic number. So, most interactions in K shell occur with low atomic number because K shell contains the most tightly bound electrons. However, in elements with high atomic number, when the energy of incident photon is sufficiently more to eject the K shell electron, then many photoelectric effects will occur at that particular energy level. Because electrons of high atomic number are bind their electrons more tightly, the elements of high atomic number are more likely to undergo with photoelectric reactions. So, photoelectric effect is approximately directly proportional to the cube of the atomic number. In summary, photoelectric effects are more likely to occur when the photon energy or low energy photon and the elements of high atomic number are seen. So, in the photoelectric effect, the important thing is atomic number and the energy. In fact, the photoelectric effect cannot take place with a free electron. If you like, we call this as a forbidden reaction. Applications of photoelectric effect in diagnostic radiology. So, first, iodine and barium are the contrast agents and they emit characteristic radiation which are energetic enough to leave the patient and result in fog formation. So, these X-rays and barium are used as contrast agents. As diagnostic radiologists, we look photoelectric effect at two ways, one good and the other bad. If you see good, the quality, starting with good, the photoelectric effect produces radiographic images of excellent quality. The quality is good for two reasons. The photoelectric effect does not produce any scatter. There is no scatter and thus it naturally enhances the tissue quality or tissue contrast. So, it decreases the scatter radiation and enhances the tissue contrast and thus the photoelectric effect produces radiographic images of excellent quality. The X-ray contrast depends on some tissues absorbing more X-rays than the other tissues. The contrast is greatest when the difference in absorption between the adjacent tissues is larger. Because the number of reactions depends on the third power of atomic number, the photoelectric effect will magnify the differences between the tissues. Because it is third power of atomic number, the photoelectric effect magnifies the difference in atomic tissues, difference in tissues composed of different elements. So, the photoelectric effect magnifies the difference in tissues composed of different elements such as bone and soft tissue. So, from this point of view, the of film quality, photoelectric effect is very, very desirable. But if you see the disadvantages are that but if you see the photoelectric effect from the patient exposure point of view, it is undesirable because patient receives more radiation from photoelectric effect than from any other photoelectric reactions. All the energy of incident photon is absorbed by the patient in the photoelectric reaction. Only a part of incident photon energy is absorbed in Compton reaction, which we are going to see later. The one more important thing is that because one of our primary goal is to keep the patient doses at the minimum, we must keep this point in mind at all times. The importance of photoelectric effect can be minimized by using high energy techniques. In general, we should use radiation of highest energy consistent with the diagnostic X-ray films to minimize the patient exposure. In summary, the likelihood of photoelectric interaction depends on two factors: energy of radiation and the atomic number of absorber. The radiation is most common, this photoelectric reaction is most common with low energy photons and absorbers with high atomic number. Photoelectric reaction is more common with low energy photons and absorbers of high atomic number. Photons usually strike tightly bound K shell electrons and they must have more energy than the electron binding energy. Photoelectric reactions are desirable from film quality because the photoelectric effect gives excellent contrast without generating scatter radiation. Unfortunately, patients' exposures are much more than any type of interactions. Thank you.